Good afternoon, this is Schweitzer. I'm looking to do an introductory, just sort of give you an overview of this lab of titration practice lab. So this is typically a lab that we do just to kind of introduce a little bit about acids and bases. Again, see how the concept of molarity works and with the titration. So our objective here, keep in mind, always keep in mind what your objectives are. Our objective is to determine an unknown concentration. So what does that mean? It means that there's going to be a beaker. You're going to take a sample of this beaker. So we have an unknown sample that will be sitting on the shelf, on the jar. It's going to be, a bigger container. Maybe this would be a swimming pool or a lake or a stream or something like that. You would take of a larger sample, you would take out of this a little test sample. So you'd have a smaller amount. This is the unknown. I don't know. I might know what it is in this case. It's going to be for us, it'll be either HCl, some sort of an acid like that, or it could be like an NaOH. Is a pretty common base that we would use. KOH could also be something that we would use. So we're going to take a certain amount of this, and I want to know its concentration. So concentration is molarity, which is equal to moles per liter. All right, so if I know the moles of my active ingredient, one of these three things, and I know the volume of this substance, then I can take that ratio to find molarity. So finding the amount of stuff in there is kind of the crux of what our lab is going to be, but the concentration of this moles per liter is the same ratio as the concentration that's in this one. So if I find the concentration of this guy, I could probably assume, unless there's some anomaly of some sort, that this concentration equals this concentration. So first step one is when we take our sample, we want to measure this thing with some amount of accuracy. So we wouldn't use a beaker to measure this out. We want to use probably a graduated cylinder of some sort. So definitely those will be sitting out, and be careful measuring out your sample. There usually is a recommended volume, and maybe we'll highlight that when we get into the technique in a minute here. So that volume will be measured. I'll know this amount right there. Okay. So now I have my beaker with my unknown substance. Keep in mind, whenever you need to determine an unknown, you need a known to compare it to. And in this case, I'm going to use, if I'm using unknown acid, I'll find a correlating known base. And I'm going to use the reaction HCl plus NaOH yields H2O and NaCl. Now this is a neutral salt. This is water, which is neutral. This is a strong acid. This is a strong base, and they react with one another. In this case, one of these guys will react with one of these guys, and that's kind of an important piece to know. All right, so I'm going to set up a burette system, titration system using a burette. So a burette is just a fancy tube that's going to have a nice little markings on here. It's going to be able to give you a start, and you'll see this on. It's all kind of set up for you on your lab sheet. Start, a finish, and then my change in volume. Now this I almost always, although it's like, is there an exception? Maybe, but I almost always put my known in the burette. You don't have to, but I do typically. There's a little valve here that's going to be open and closed just to drop this stuff out. Place your stuff below here, and let's take a moment and just talk about how this works. Make sure this is rinsed out and then rinsed with the chemical you're going to use. Okay. You can write down your start amount that you get, and you drop it in until you see some change occur. Now we're looking for a visual change. So what happens here, let's take a moment, just take a look at a beaker level, what's happening here. So let's just say, for example, that my unknown is an acid. Okay, so an unknown acid. And let's just say hypothetically that the acid, I'm going to make this just a greens. Okay, now they're not green. This will be a clear solution, H plus, Cl minus. It's a strong acid, so it is going to be completely dissociated. We'll learn more about acids in the next chapter. Anyway, so then I'm going to drop in. Let's just say I drop in. Let's go with a blue NaOH. Now I don't know exactly how many molecules I'm dropping in here of the NaOH, but I do know that I'll have the volume. I know the concentration, it's known. So molarity equals moles per liter, or molarity times liters equals moles. So when I multiply this two together, I would get the number of moles that I'm going to be dropping in here. All right. So I drop it in. The Na plus is a spectator. It does nothing. But I drop a hydroxide in, and the hydroxide will immediately attack the acid, and it forms a neutral water. At this point, I am still acidic because I have acid left over. Then I drop in some more NaOH, and eventually I get to the point where my last hydroxide is attacked or neutralized the last H plus ion. It's following the reaction of NaOH plus HCl yields H2O plus NaCl. This is referred to as the ionic equation, the molecular equation. But the net ionic is going to be just what happens, and that's going to be OH negative plus H plus yields water, and that's kind of what's happening here. That is what's happening here. So then all of a sudden I run out of acid. Then if I drop, and invariably I drop in one more little drop of hydroxide, and I got a cation here. This thing is now basic. It goes from being acidic to neutral, very short period actually, to being a little extra hydroxide, and I am basic. So I'd like to be able to stop right here. This is going to be, for this particular lab, this is our equivalence point. So the question is, how do we know? So if I stopped right at my equivalency point, I'd have my volume that I added times the molarity that I added gives me my moles that I added. And you'll note that they react in a 1-to-1 ratio. So if I know the moles of NaOH that I dropped in, if I know the moles of the NaOH I dropped in, that equals the moles of HCl that were there before, the original H. If there were two H pluses here before, so I have to drop in two hydroxides to match them. So if I know how many of these I dropped in, I know that this is the original I had. And if I take for molarity of my unknown, what do I need? I need the original volume, which of course I measured. Okay, I have that. I have the original volume. If I take my original volume, divide by my original moles, I'll get my original molarity. Okay. And that's what I want. Now I'm destroying my sample in the process, but remember that this sample I took is reflective of a larger sample, lake, stream, pool, whatever. Okay. All right, so the next question might be, how do I know when I've reached equivalency? Okay. So how do I know this is all clear color solutions? You're never going to know. You need something to indicate to you that these two things are now equal, that this has happened. Okay? How do I know? Well, I have a couple options here. One is I can stick a pH meter in here, and we will do a lab on that eventually. But now, rather than that, we're going to use what's called an indicator. So an indicator is a chemical that changes colors. Chemical that changes colors with pH. The chemical we're going to use is going to be called phenolphthalein. It's a long word, you know. It's like Thalien. You can look that word up. Phenolphthalein. Thought I had it right. It's pretty close. Phenolphthalein. Now, phenolphthalein is a very potent chemical. So before you start, literally you're going to drop in just like 1 or 2 drops. You don't need more than that. And when it goes in here, originally it's sitting in a beaker that's just got acid in it. In acid, phenolphthalein is clear. That's important to remember. But in the end, you're going to have a beaker that's going to be basic. And it turns pink, or kind of a red color like this particular color that I'm showing. So in this case, this stuff is clear in acids, and it is pink in bases. It's not perfect, but it's close. So what we would do is we would titrate this in, and it's going to start clear, and we want to titrate until we just turn pink, and not a lot, just like 1 drop turns it pink. We stop right there. We're going to assume that's very close to our equivalence point. Now, if you reverse situation, you would start with a beaker that's a base. It would start pink, and it would become clear. In that case, 1 drop turns it clear. That's how we know where our equivalency point. Let's take a quick moment and just peruse the math a little bit. Now, on this thing here, okay, what do we need to know? Volume of known. Okay, this is also a concentration of known. So before we start the lab, there's going to be a known solution. I want to know, is it HCl, and what is its concentration that it's listed as? I need to know that. That's what I'm going to put in the burette. Then my unknown. Okay, if this is HCl, then this is going to be NaOH likely, and I'll have a recommended volume. The reason why I have a recommended volume is simply because in the burette, if you run out, then you gotta start over, and it would be fine. But in this case, just to make sure you don't run out, I just give you a heads up that don't take more than 10 or 20 or whatever. Could be somewhere between 5 and 20 milliliters. At that point, I have this guy right here. Okay. I have a start, I have a finish, I have a change. Most often for this type of calculation, or we do there's a known unknown table. Now keep in mind, it's really important, I made this up. Okay, Mr. Schweitzer made this up, and no one else is going to really know what. It's just a table. Okay, it's not a substitute for work. So I have molarity, moles, liters. The known will have a known concentration, that's why it's known. It will have a known volume. This will come off the burette, which is right here. And then the unknown will also have a volume, and at equivalence, these two are equal. So I know everything here except for this guy right there. Show your work along the side, that's required. The last thing you want to just kind of chit-chat about here is generally just keep in mind how this thing works mathematically. If I have a reaction of HCl and I have NaOH, and let's just say hypothetically that I have in my bottom beaker, I have my NaOH, and I don't know its concentration, and I'm going to drop into this thing my known HCl, 0.1 HCl, and I don't know what this is, but let's just say I have 15 milliliters of it. I measure that out with a graduated cylinder. And I drop in, I start from my start, let's say my start's at like 10, and I go down, titrate until I get to about 25. Okay, and then I have reached my color changes, and I've reached my equivalency. Let's walk through this once. So I want to find out the moles of this guy. So my known table, and my unknown table, I'll walk through this quickly here. So what is my known? My known molarity is 0.1. Okay. My moles I'm going to figure out. My volume, start minus finish, is 15 milliliters, 0.015 liters, or 15 milliliters. Then, what do I have below here? Well, that's also 15 milliliters, with 0.015 moles per liter. And at that point, 15 milliliters. Let's solve this out. Molarity equals moles per liter, and I want to find my moles. So molarity times liters equals moles. 0.1 times 0.015 equals 0.0015 moles. 0.0015 moles. And this is equivalent. Always the same. Well, it's the same by the stoichiometric ratio, which in this case is 1 to 1. 0.0015. Now you notice this. I have the same moles. I have a same volume. So I have the same concentration. So whenever I look and compare these two concentrations, I look closely at the volume. If the volume is the same, then the concentrations, the moles are always the same. If the volume is the same, then the concentration is the same. If, let's say, for example, this volume is larger, okay, molarity equals moles per liter. If the volume is larger, that means that the same number of moles in a larger volume, then this has to be less. That means this is less than this. This is less than this. If the volume is smaller, then the same number of moles in a smaller volume means this thing's larger. So that means this guy here is larger than this one. So there's a really important general math idea here, big picture idea of comparing these things. All right. Good luck with your conclusions. At least your calculations. Typically, we don't have a conclusion for this one. Thank you very much.